Hi, I'm Miss Hall, and this is Lesson 68, Writing Recursive Rules for Non-Arithmetic and Non-Geometric Sequences. Example 3, Writing Recursive Rules. Write a recursive rule for each sequence. Okay, so as the topic states, these are non-arithmetic and non-geometric sequences. So when we look to writing rules, fortunately, we don't have formulas to use. There isn't a common difference. There isn't a common ratio. So now we have to search for patterns. In A, you've probably seen this sequence before. 1, 1, 2, 3, 5, 8, 13, 21. It's the Fibonacci sequence. And we can't write the Fibonacci sequence as an explicit rule. We can't just jump to any term, as far as I know. Rather, the Fibonacci sequence is when you add the previous two terms. So you'll see that we get 2 because 1 plus 1 is 2, and then 3 because 2 plus 1, and then 5 because 3 plus 2. So to write this as a recursive rule, we have to write out the first two terms. A sub 1 is 1, A sub 2 is 1, and now the rule is that you add the previous two terms. So we know how to write the previous term, A sub n minus 1, and how you write the term before that is A sub n minus 2. So for this recursive rule, you actually need 3 equations, because you need to know the two terms that you're going to add. Now B. This pattern is tricky to see, so I'm going to start by writing my domain and seeing if that helps. Okay, so the first term is 1, the second term is 2, the third term is, first term 1, second 2. So what I'm seeing is that 1 times 1 is 1. 2 times 1 is 2. 3 times 2 is 6. So if you multiply the x and the y, you'll get the next term. If this is the table, you'll get the next y value. Your book actually finds a way to make this easier, and it's easier if I start by labeling the domain as 0, 1, 2, 3, 4. Because then what I do is I take what I'm going to call x, right, if this is the table. I'm going to take the x value times the previous y value to get the new y value. The x value times the previous y value to get the new y value. So here, my first term is going to be my 0 term. So my 0 term is 1. It's part of the trick of this problem. Setting the first term to be 0 makes it easier to write this recursive rule. And now here's the second trick. So the rule is n, your domain, times A sub n minus 1. Yeah. Right. So not only is it helpful to start with the 0 term here, we now see that you can include the domain or the n value as part of your rule. Example 6. Solving a real-life problem. A lake initially contains 5,200 fish. Each year, the population declines 30% due to fishing and other causes, so the lake is restocked with 400 fish. Write a recursive rule for the number of fish at the start of the nth year. For a recursive rule, we're going to have at least 2 equations. We're going to have the initial term, which we start with 5,200 fish, and now we're going to write the rule for how you get each subsequent year. Okay, the population declines 30%. So instead of being 100%, keeping the population exactly as is, it declines 30%, which means the population is 70% of the previous population. So I can write that as you take the previous population times 0.7, and then the lake is restocked with 400 fish, so plus 400. That is the recursive rule. Multiply by 0.7 and add 400. Part B, find the number of fish at the start of the 5th year. So because I have a recursive rule, not an explicit rule, I can't just go to year 5. The recursive tells me I have to figure out year 1, year 2, year 3, year 4, and then 5. So I know the first year is 5,200. For the second year, I can use my recursive rule. I'll take 5,200 times 0.7 plus 400 to get 4,040. Then for the third year, I'll take 4,040 times 0.7 plus 400, and that equals 3,228. For the fourth year, can't skip, I take my previous amount, so 3,228 times 0.7 plus 400. That equals 2,659.6. And finally, my 5th year, take my previous 2,659.6 times 0.7 plus 400, and that equals 2,261.72. And we're talking about fish, so let me approximate. That's about 2,262 fish at the start of year 5. Part C. So here's how I was putting it in my calculator for part B. I start with 5,200 fish times 0.7 plus 400, and that's where I got 4,040. And now I can take that answer times 0.7 plus 400. That gives me year 2, year 3, right? And then I press enter. That gives me the subsequent year. That's year 5. So I can keep clicking, and I'll see if these numbers stabilize around a certain value. At a certain point, if the fish population stays, it looks like it's staying around 1,300. And yeah. Right, okay, so I've gotten several of these. So I'm going to say that the fish population stabilizes around 1,333 fish, because each year is changing by hundredths or thousandths of a fish. So it's pretty much staying at this 1,333 number. So that's how I'm going to answer part C.